So I'll be talking about Quokka, new multiphysics code for star formation and astrophysics. And I started creating the code when I was a postdoc in Australia. So the mascot is a quokka, and here is our logo. A quokka is a marsupial, native to Australia. It's very cute. But yes, it's a real thing. Yeah. Yeah, and it's so as a marsupial, its children are carried in its pouch, and I thought this was a nice metaphor for how um, patch-based AMR works. And yeah, so this is on behalf of the entire Quokka development team, who are all listed here. So the target application for this code, so there are several AMReX-Astrophysics codes, and we've heard from a couple of them. So we're targeting much finer resolutions than, say, NICS. So I guess any astrophysics in the Newtonian limit where we have particles representing individual stars. So we're not resolving the internal structure of stars. We're not blowing up stars like Castro. We're not representing cosmological volumes like NICS. We're sort of, well, we are definitely intermediate in logarithmic space in terms of the box size and resolutions we care about. So we care about things on the scale of parsecs down to AU scales in some cases, but not below that. So our target applications are primarily galaxies, where we have particles for individual massive stars. The whole star is just a single particle. And star clusters, where we have sync particles. The particles can accrete and gain mass as they form. So the original science motivation was to simulate a star cluster like this. So the initial conditions are very idealized, but this illustrates the kind of application that we care about. So we have some molecular cloud in a galaxy, and we're treating it in isolation. And we have open gravitational boundary conditions, which AMReX really helps us with. And then we're adding some turbulent velocities and watching it collapse and cool and fragment, the gas collapse and cool and fragment until it reaches, the max level of refinement. And then we say, aha, a star is born. And then that star particle can continue accreting mass, in a useful approximation, we hope, to how stars are actually formed in the universe. So this whole simulation, this whole box is about 1 AU, which is about 3 light years on the side. And then the maximum resolution we hope to go to is about, 1 parsec, which is about 3 light years on the side. And then the maximum resolution we hope to go to is about 5 orders of magnitude smaller, down to 1 astronomical unit, 1 AU scales, the distance from the Earth to the Sun. So the other science motivation that we really care about is simulating whole galaxies. So we're not simulating the formation of stars, but we're saying there's some idealized initial condition for the galaxy. We're simulating all the dark matter in the halo surrounding the galaxy. And then once we have a mass that's Chins unstable, it collapses and we create a star particle. And then, sometime later, it blows up into a supernova. So you're seeing a galactic wind being created by all the collective supernovae that are blowing up. You can see basically each supernova event, I'll play that again, creates a little blast that you can see coming out of the galaxy and creating a little hole in the density distribution you can see on the right. Then all the stars that have formed are all the particles plotted as black dots. And there are lots of, this is a model for our own Milky Way galaxy. And coming online in the next decade will be, for instance, the square kilometer array, which will have, unprecedented resolution of our own galaxy to probe its gas content, like you see here, as well as its magnetic fields. So this simulation was run, I ran it, from Sunday to last night on 1 Frontier node. And we're applying for Insight time to do this at 16 times better resolution on 1,000 nodes. The full simulation will have 12 AMR levels. It's hard to scale MLMG to that many levels, but we are really trying. If you have any ideas, let me know. So we're solving the equations of radiation hydrodynamics. So hydrodynamics, we all know about. Radiation transport, we're evolving the equation for the energy density and the flux of the radiation field. And the reason we care about that is for 2 different reasons. For galaxies, we care about ionized gas bubbles produced by the ionizing radiation of massive stars. These produce so-called H2 regions for ionized hydrogen. So we need to follow some approximation of radiation transport to capture their dynamical effects on the galaxy. And we also care about the dust re-emission in molecular clouds. And so on for star formation simulations, we care about following the infrared radiation inside the star cluster. So our numerical methods are a little bit different from some AMReX codes. We have a Runge-Kutta integration using the RK2 SSP or Hund's method. And then we use ppm reconstruction in density, velocity, and specific internal energy. And the reason we do this is it's really robust and seems to work better for our problems which have supersonic turbulence in a lot of cases because we have really strong radiative cooling. So yeah, we have Mach 10, Mach 20 supersonic turbulence, and yeah, the unsplit Godunov method kind of blows up when we try that. So yeah, we use method of lines, and even doing that, it's not quite enough. We get negative density cells, so we have a fail-safe limiter inspired by the flux-corrected transport method to drop to first order in space and time in troubled cells. So we have our own custom RK integrator because we have to do this dropping to first order. So we can't use the higher order RK methods in AMReX, but second order is good enough for our problems. We do have somewhat complicated bookkeeping, and this does make things a bit slower because we need extra communication in each RK stage to sync the fluxes when we drop to the first order fluxes to ensure that neighboring grids, faces on neighboring grids use the same first order flux when we drop the fluxes. Some other probably relatively unique things about our methods is we have both low Mach and high Mach flows, very, very low and very high Mach flows. So we have low Mach corrections to our Riemann solver, to our HLLC Riemann solver, produces the correct scaling of pressure jumps and the incompressible limit. And that's for low Mach flows. And then for high Mach flows, we have a dual energy method. So we evolve an equation for the internal energy of the gas for the hypersonic parts of the flow. Formally breaks conservation, but only by a fractional amount, and the shock speeds we find are still correct in practice. So we also use a relatively special method, although more common in the star formation community, the galaxy formation community, for radiation hydrodynamics. So we actually evolve the radiation transport equations explicitly, and the source terms implicitly. So the speed of light is very large, so we don't want to use a traditional explicit method because the time step constraints would be prohibitive. So we artificially reduce the speed of light to a factor of 10 or 100 of the maximum fluid velocity. And so this is the so-called reduced speed of light approximation, which has been used in astrophysics for a couple of decades now, and makes it feasible to use an explicit in time integration method. This doesn't work in all regimes of radiation hydro, but it works for the regimes we care about the most, with one exception I could talk about in the Q&A session. Yeah, so it maintains a qualitatively correct solution, more scalable than implicit methods, perhaps better suited to GPUs, although Hyper is getting better. But it's really the scalability that we care about for big galaxy problems, where we really care about getting the expansion rate of the H2 regions, the ionized gas bubbles around stars, correct. And even reducing the speed of light, because the source term and the transport term are both modified, we get the expansion rate of H2 regions correct. I'll skip over that. We get great GPU performance with AMReX, typically 10 to 20 times faster on GPU compared to CPU, which has been great. And we also get, at least 90% scaling efficiency on Frontier when we turn on GPU-aware MPI. Also awesome. Thank you for that. So we get great performance. I/O performance, some issues The AMReX-IO is usually great. We've had some scaling issues with particle I/O. I know Andrew and I have talked about this, but that limits our weak scaling a little bit. We're considering using OpenPMD with Adios 2 for our production runs, but we have to implement that for checkpoint and restart. So we do hydrodynamics, radiation, self-gravity using the OpenBC solver for open boundary conditions. We're using the microphysics library as part of the AMReX-Astro suite to do chemistry solves in each cell. And we have dark matter particles and star particles, and magnetic fields hopefully soon. So one thing I want to talk about in terms of solving chemistry networks. So unlike NICS, we use a different way of solving the chemistry borrowed from Castro. So we have a chemical network in each cell describing the abundance of chemical species as a function of time. This is like the fraction of ionized hydrogen, neutral hydrogen, molecular hydrogen in each cell. Potentially many more species depending on how detailed of a model we care about. So a set of n coupled ODEs in each cell, but each cell is independent. And we operator split. So do we rewrite VODE? Do we use CVODE? I tried using CVODE, but it was really slow. So I tried microphysics, and it worked a lot better for us. So what microphysics does, I don't think there are any other codes here that use it that I know of, but it's a C++ board of VODE plus some other cool stuff for time integration and math utilities. It involves a chemistry network or a nuclear network independently in each cell. Even though each cell requires a different number of substeps to solve the system of ODEs, thread divergence happens on the GPU. It's still fast. Don't fully understand why, but it still works well in most cases. The right-hand side of our networks plus Jacobians are generated using SymPy's C++ code generation tool. We did this before we learned about autodiff, so we probably wouldn't do that again. But it works. We do have extremely high register pressure for some of our networks with lots of species. We have very weird reaction terms over many orders of magnitude in density and temperature. We have extremely high register pressure for these kernels. Rockham didn't compile it correctly until 6.3, but fortunately it now does. So we're very thankful for that. So target user communities. Currently we have people in the galaxy formation evolution community and the star formation and interstellar medium community using our code. There's some interest from people who do protoplanetary disks and planet formation, but no active users that I know of. But all astrophysics. So in terms of future code development and the trajectory of the code, some users are interested in doing zoom-ins from cosmological AMR initial conditions, where we don't really care about the statistics of the cosmology or the cosmological volume itself, but just using the cosmological environment essentially as a boundary condition on very coarse levels to solve for the accretion of gas onto the galaxies that we care about. So that's something we're interested in adding in the future. We're working on adding constrained transport MHD. It's very important in star formation and the interstellar medium. And potentially for people who work on protoplanetary disks and planet formation, there's a special algorithm to reduce the time step constraint for orbital advection when you essentially have an advection speed that dominates all the other signal speeds in the problem. You can analytically remove it in the integrator. So we're potentially considering adding that. Future code development, we have a group interested in adding a dust model that's important in all of these applications. Cosmic dust seems to affects almost everything in mysterious ways. Cosmic rays, we're very interested in cosmic rays, but that depends on adding magnetic fields hopefully soon. And Monte Carlo radiation transport is potentially something of interest for star formation and protoplanetary disks, but that's probably a few years away. So yeah, we can do a lot of physics, and we can get a lot of resolution on problems like blasting an interstellar cloud from a shock from a supernovae. Um, and I think there are a lot of exciting applications that we'll have in the future. Thanks.
All right, questions for Ben?
Maybe I just missed your talk. So for your reaction networks, you evolve in the hydro state, or how you handle that?
How we handle what? What part of the reaction network? So it's operator split using strong splitting. Yeah. So I think our largest network has like 15 species, 14 species currently. But yeah, the complexity comes in the form of the reaction terms because we don't have a simple standardized fitting function for all the reaction rates.
One of your slides said miscompile. Fixed or miscompile.
That's right. The compiler just generated code that was totally wrong. Yeah.
So I'm part of the Pele project. We have Pele Physics that does a lot of chemistry as well.
Yeah.
So I'm curious if you ever looked into that and seeing if some of the solutions that we tried to implement would work for what we're trying to do. Because our networks, you said 15 is big. That's small for us. Right. We're
Right.
hundreds of species. So I'm wondering, we also have kernel pressure, register pressure issues. So I'm wondering if you ever had a chance to look into that.
Do you know how it compares to what's in the Astro Microphysics?
I've never heard of it.
Okay. Okay.
So.
Yeah. So I. Oh.
So the AMReX-Astro Microphysics, what Castor was using, which is specifically they had their version of Bode that put all the GPU stuff in, and then eventually they made it more C++, basically.
But it's basically Bode, and you guys have different algorithms.
We have different integrators. We have explicit RK, but we also have sundials and magma in there.
Yeah. So we use Vode that operates independently. So each GPU thread integrates a separate network independent. Each cell is treated independently. Yeah. Which is what you do.
The other thing is the C-Bode one is driven on the CPU, and the Bode, the AMReX-Astro Microphysics, it's driven on the GPU. So like C-Bode has like, here is your vector, and we're going to send to each cell on the vector to do each of the operations. But this one, like everything continuously goes on the CPU, I believe.
Yeah, so that was the point I was going to make. Yeah, so we call the integrator from the GPU thread, from each GPU thread.
John, you only be setting up, and maybe there was one more question, or.
So I'm going to make a statement real quick, which is you had some neat movies, and I suspect we're going to be seeing a lot more. We would love to have those on the AMReX gallery. It's full attribution to you. It's just a place to showcase movies. So
Absolutely, I'll send it to you.
contact us in Slack and stuff. I make Andy do the actual uploads. So you can send me stuff on.
Let's thank everyone one more time.
Thanks.